So we will find the volume of a solid of revolution using the disk or washer method, which technically they are the same, but that's going to depend on how the region of integration is set. For example, if it's a whole solid, well then we will be looking at a disk. If, for example, we have a solid bounded by two regions and having like a hollow space in the middle, in the center, well, then in that case it's the washer method. But essentially it's the same setup at all. All right, so well, what's the picture anyway? So let's start with that. Cartesian plane, and let's have some function f of x, you know, whatever function f of x, and let me make it a little simpler. And what we're going to do in this case is we will rotate this region about, well, let's look at the simple case in which we rotate about the x-axis, so when we construct the formula it's easier in those terms actually. Well, so you might have seen those ornaments they sell at Party City, you know, that you can open and then paste or stick the two endpoints, right? And then hanging like they have like shapes of bells, hearts, and something like that. Well, you can think of a solid of revolution as having a region like that. Well, actually, I used to have one of those and wanted to bring it, but I didn't. I couldn't find it, just so I can show you what we are essentially doing. So this is what we're going to obtain. So let me do this in a like a dashed, and we're gonna have something that's gonna look like this. Now let's make it look like a solid. Alright, so we have a solid of revolution here. So we created, rather than a picture in 2 dimensions like we did last time, no, so this is a picture in 3 dimensions. And this will come back later when we will find the area of the surface generated, not the volume. It's going to be a similar setup. Okay, so coming back to the original idea about the integral, recall that the integral would give us the area under the curve, all right? And well, the way we got the area under the curve was by partitioning the region. Well, at the beginning you did it, well, partitioning a region between 1 and 2 for a simple case in 4 rectangles. Of course, you were not going to get the actual area. You needed to add infinitely many areas of rectangles to get the actual area. But when it came to finding areas of rectangles to approximate the area, what we did is to find one element in the partition that contained delta x, which is the length of the rectangle, and f of x, which is the height of the rectangle. And then so you find the area of that rectangle plus the area of the next rectangle plus etc. to get an approximate result, and then come up with, or rather incorporate, the infinite Riemann sum to get the actual volume. Well, in a similar way, so what happens when we rotate this? This will be no longer a rectangle. So think of a rectangle being rotated. What geometric shape would that be? It's a cylinder, right? A cylinder, it's rather a really large radius but a really tiny height, right? That it looks more like a disc. So that's why we're going to call this the disk method. So when we rotate this, we're going to obtain a disk. And let me draw this disk over here. So that's the circle being rotated. Let's make it look 3D. Hopefully it looks 3D like this. And well, so this length, the thickness of the disk, it's going to be the differences of the x's. That's the delta x. So we have And let's call it delta x sub I, because it could be the delta x of the first disk or the second disk or the fifth disk, the ith disk. You know, that's the arbitrary disk that we obtain, in the same way that we chose an arbitrary rectangle to construct the formula. And then, well, the radius of this disk, it's actually going to be the height of the function from the x-axis to whatever value of y on the function, and that's, let's just call it r of x. All right, let's just call it r of x. Okay, so we're going to start from area, then we're going to find volume, and then we're going to get the integral. To begin with, let's get the area of the circle. Well, area of the circle is pi r squared. All right? And if we write this as a function of x, that's pi big R of x squared, which is this function right here. We are describing the radius of the circle in terms of the function that we are integrating, right? And well, we know that volume equals area times the circle times height. Well, in this case, we're going to go back to the formula of the volume of a cylinder, even though the shape looks more like a coin, like a disc, but ultimately a disc and a coin are cylinders. But the thing is, cylinders are usually taller than they are wider. Unlike coins and discs, they are wider than they are taller. But it's the same geometric shape. To find its volume, we use the same formula. All right. Well, so we have a formula for the area in terms of x. That's pi r squared x, and the height of the cylinder. That height is going to be the thickness of the disc in this case, which is delta x sub I. All right. Well, of course, we can find the total volume, let's say from A to B. Well, by adding all these partitions, by adding those volumes of every single partition, 5, 17, 291. Well, of course, in this case, we would be adding infinitely many of them. Well, actually, this is not equal. This is supposed to be approximately, because we're going to go from I equals to 1 to n. And again, n can be any number. But if n is a finite number, like I mentioned before, 17, 25, 150, well, that's an approximated volume, not the actual volume. If we want the actual volume, not the approximate, then you want to add infinitely many of those tiny volumes. That is, find the limit n approaches infinity of the sum of every single little volume here. And well, by the definition of Riemann sums, this is nothing other than the integral from A to B. That's pi big R squared of x dx. Okay, so that's our formula to find the volume of a solid revolution. But of course, I mean, I use the letter R here for radius to describe the function, the radius of the cylinder in terms of the function. Of course, we're going to go with, okay, let me take the pi outside of the integral, A to B, f of x squared dx, because ultimately, yes, this is R of x, has a radius, but that's ultimately a function f of x. Okay, and we're going to do f of x maybe minus g of x, and then later we are going to redo this setup, but for the rightmost minus leftmost, in the same way that we did it last time with the areas as well. All right, so let's have a look at one example. Just like last time, we're going to warm up with one example in which we are given everything. So they're giving us the function that we will rotate. They're giving us the bound, so we don't have to find anything. So I think this is a good one to start with. Okay, so let's see. Let's draw the Cartesian plane and plot the region. So they're asking us to find the volume of a solid obtained when rotating the region bounded by y equals the square root of x. And well, let's draw the graph of the square root of x, which looks like this. Okay, that's one to begin with. The x-axis is one of the bounds. All right, and x equals to 4. So the vertical line, 1, 2, 3, and 4. All right. But notice we're not finding the area. We're finding the volume. So we will rotate, by the way, something I needed to write over here, rotating the region about the x-axis. All right. So when we rotate this, okay, that's fine. We're going to get, whoops. We're going to get this solid right here. All right. Going to get that solid of revolution. And well, let's set up the problem in this case. Well, so you can still think of a taller or upper minus lower, rather top minus bottom. We're gonna do something about this in more detail in the following examples. In the meantime, well, so let's set up volume equals pi integral from a to b of f of x squared dx, and in this case the limits of integration, we can see them from the graph. The lower limit is the origin is 0 and the upper limit is 4. Oops. And the region that we're going to square is square root of x dx. Well, in this case the radical cancels the square. We're left with only the integral of x. So pi integral of x dx, 0 to 4, the integral of x is x squared over 2. From evaluated from 0 to 4, the remaining part of the problem is only fundamental theorem of calculus, evaluate at the upper limit and minus evaluate at the lower limit. So this will be pi times 4 squared over 2 minus 0 squared over 2, and 4 squared, which is 16. 16 over 2 is 8 minus 0. That's 8 pi. All right. So that's an example to begin with, to warm up, so you can see how the formula works in action in a very simple region of integration. Of course, these are going to get a little bit more elaborate as we move on through the level of difficulty of this. Well, let's look at example number 2. So they're asking us to find the volume of a solid obtained when rotating the region bounded by y equals to x, y equals x squared about the x-axis, and this is it. This time they're not telling us any limits of integration, they're not giving us any additional information, but the mechanics are very similar to what we did last time. What do we do when they're not giving us any limits of integration? set them equal to each other, right, and find the points of intersection. That's going to give us an idea of what the limits of integration are in this case. So that's what we're going to do. But in the meantime, as usual, as always, we have to graph. So we have the line y equals to x, the diagonal line. Oh, me, I think it's too big. And also we have the parabola y equals x squared, which is going to look like this. And actually it's going to intercept like this. Okay? And then, well, the solid that we are going to obtain, taller or top minus bottom, the top function is the linear function and the bottom function is the parabola in this case. Now, what is this generating? Well, this is generating the following region. So it generates this solid right here. It's kind of hollow in the middle. All right. But not that hollow. Actually, it's solid at the part where the region it's at the origin. All right. So let's set up the integral in this case. So unlike the first example, well, we will extend, like I mentioned before, we're going to extend this idea to the top minus bottom thing. So in the same way that we did it for areas last time. So volume in this case, that's pi, integral from a to b, and that's the top squared minus bottom squared. All right. Typically f of x minus g of x. Right. It's very the same as we did with areas. We're going to do it with volumes as well. So in this case, so volume equals pi, integral, limits of integration. Let's go back to the limits of integration. Let's set the two equations equal to each other. That is x squared equals to x, and then recall that we don't divide by x. We discussed this last time. We have to have all the terms on the left hand side, because when we divide by x, we are potentially dividing by 0, and we would be turning that equation into a first degree equation, giving us only one solution when we actually have a second degree. So x squared minus x, then by factoring we get x times x minus 1, x equals to 0, and x equals to 1 by using the zero product property. So the limits of integration are going to go 0 to 1. So that's going to be, in this case, using the top squared minus bottom squared. So again, the top function squared is x, and the bottom function squared is going to be that we square. It's going to be the parabola, because again, if we look at the picture, the upper bound is given by the linear function and the bottom part is given by the parabola. So from here, let's simplify the integral. That's the integral of x squared minus x to the fourth with respect to x. And while the integral of this, it's pretty straightforward. Again, that's another general power rule problem. That's x cubed over 3 minus x to the fifth over 5, evaluated from 0 to 1. All right? And again, the remaining part of the problem is only the fundamental theorem of calculus, evaluate up to upper limit minus evaluate at the lower limit. But see how nice this result will be, because one of the limits is 0, and in this case it works to do what we did last time with just writing a big 0. I'll show you. So that's 1 cubed over 3 minus 1 to the 5th over 5 minus big 0. Do we agree with the big 0? Because, I mean, plug in 0 to x cubed and x to the 5th, it's just going to get zeroed out. So this is fine. And well, 1/3 minus 1/5, that should be pi times 2 over 15, which as a final result, that's 2 pi over 15. I would like to go back to the first example, and just so we can connect the idea of the top minus bottom to a really simple region like the one we just did for example number 2. I mean, even though I didn't do the top minus bottom for example 1, there really is one. So if we rewrite, for example, this integral, what is the top function in this region? The square root of x, right? So volume equals pi integral, what was that? From 0 to 4. That's the square root of 4, I mean the square root of x squared minus, what's the bottom function in this case? 0, right? But I mean, do I really need to write that 0 squared? For a region this simple, it's not necessary. But ultimately that 0, it's there in spirit, if you will, right? Just so we can connect with the idea of top minus bottom in a more generalized way. So let's see what's next. Okay, they're asking us to find the volume of a solid obtained when the region bounded by y equals 2 over x, the y-axis, y equals to 1 and y equals to 4. So this time they're giving us a lot of information, but in this case be careful because this time they're asking us to rotate the region about the y-axis. Okay, when using the disk method or the disk and washer method, and we want to rotate about the y-axis, this means we need functions of y. Alright? This is key right here. Disk and washer method, the rotation goes about the x-axis, functions of x. The rotation goes about the y-axis, functions of y. So let's see. How do we graph this function? Well, what does the graph of y equals 2 over x look like? Any ideas?
Is it a circle?
Like 1 over x? Yes, like 1 over x, except that that is a 2, making it a little stretch, you know, by a factor of, that's what the coefficient do. Alright, so y equals 1 over x. What's the graph of y equals 1 over x? Any idea? Yes, looks like this. Yep, with a vertical asymptote at 0 and also a horizontal asymptote at 0. Alright. Well, but in this case, we're not going to draw the whole graph on both tails of the graph, because in this case, we are being bounded by the y-axis, y equals to 1, y equals to 4. So we will only plot the part of the graph that is in the first quadrant. And well, to draw the graph of 2 over x is just going to turn a little stretch, you know, so rather compressed, not stretch, compressed. So let's plot the region. So it's the y-axis, one of the bounds, the graph, and what else? They're telling us y equals to 1 and y equals to 4. All right. But in this case, we're not going to rotate this region about the x-axis, but rather about the x-axis, but rather about the y-axis. So we're going to do the rotation like this time, and this is going to generate the following solid, like this, and that's going to generate this solid, right? Like a volcano. It looks like a volcano, right? Like a funnel, like an upside down funnel. Alright, so let's find the volume, but actually, like we mentioned before, since we are rotating this region about the y-axis, we need functions of y. So this function, y equals to 2 over x, we need to redefine it as a function of y. Well, all we have to do is solve for x to get a function of y. When we do that, so y equals 2 over x, multiply both sides by x to get x, y equals to 2, and x equals to 2 over y. Essentially the same function, just interchange the letters x and y. And I think from here we're ready to set up the integral. But in this case, careful, because in this case for our volume, it's defined in terms of y. Let's call this g of y, or rather f of y, dy squared. And instead of integrating from a to b, we're going to integrate from c to d, in the same way that we set it up for the area between two curves. Functions of x, a to b, functions of y, c to d. So that's the integral. In this case, well, they gave us the limits of integration from y equals to 1, y equals to 4. That's if you want to label this, which is fine. Let's call this the c, and let's call this the d. So, oh, I forgot the pi here, and that's from 1 to 4, and that's 2 over y, quantity squared, dy. So let's simplify this. 2 squared over y squared, that's going to give us a 4 in the numerator, a 4 that we can actually take outside of the integral, and that's going to be 1 over y squared dy. You know what, let me do just a pi, that's fine. And let me do one step at a time. So that's 4 pi, integral from 1 to 4. Well, we cannot integrate this 1 over y squared while it's in the denominator. We need to write it in the numerator, in this case with negative exponents, so we can use the general power rule of integration. And from here, I think we're ready to go about the integration. So the integral of y to the negative 2, and be careful here because we add 1 to the exponent and divide by that new exponent, so that's going to be 4 pi. When we add 1 to negative 2, we get negative 1, but don't forget to divide by negative 1. And that gets evaluated from 1 to 4. Of course, let's clean up these negatives, both the one in the denominator and the one on the exponent. So that's going to be negative 4 pi, and that times 1 over y, from 1 to 4. And as usual, upper limit minus lower limit, that's the fundamental theorem of calculus. So that's negative 4 pi, and that's 1 over 4 minus 1 over 1. All right, and well, to combine these two fractions together, that's the same as saying 4/4. And 1/4 minus 4/4, that's going to give us negative 3/4. But times the negative that we had outside from the integration, it becomes positive. So be careful with these results, because at some points in the process you will see some negative signs, but ultimately all these results have to be positive, well, because of the physical context of a volume, which has to be a positive result, right? So that's 3 pi. You know, the force cancels, negative times a negative becomes positive, and that is a volume, our volume. All right, so far so good? Okay, other more involved type of regions here. Well, for the examples that we just did, we have been rotating these regions about an axis itself, whether this is the x-axis or the y-axis. However, more let's say complicated situations will require to rotate a region, but in this case about somewhere else than an axis itself. And well, so in this case, well, we're going to set up the integral. I'm going to give you the final answer. I'm not going to go through all the details of the integral, because here really the most important part of the problem is the setup. So you can actually think of this as exam questions in which you will be required to only set up the problem, not even to evaluate it, because well, once you see the integrals that we are going to get, yes, they're still doable. However, they're time consuming, and on a 2-hour exam, well, time is valuable. So for sure, this one problem like this, if we were to do the whole thing, would take about 15 minutes or so in lecture. But when you are on the exam, it's different, because you're pressured with time, you're thinking of other topics that you're also being tested on. So, well, let's see. So this time, we want to set up an integral that finds the volume of a solid obtained by rotating the region bounded by x squared and y equals to x. I mean, very simple functions. But in this case, we want to rotate about the line y equals to -3. Not in this case, not the x-axis, which is y equals to 0. This time is the horizontal line, y equals to -3. Okay, let's sketch. So usually we would sketch the region like this, right? So that's the line y equals to x. It's a little steeper than y equals to x, but I mean, it's only a picture, it's representative. It's, as long as it's a straight line, that's fine. And on the other hand, what do we have? The parabola y equals x squared, all right? However, be careful. In the previous problem, we did this. Rotate about the x-axis, which is y equals to 0. Not this time. Not this time. So this time we will go to the horizontal line, -1, -2, and -3. And I'm going to draw a dashed line that represents the axis of rotation. And of course, to give it a character of rotation to this, let me do this symbol right here. Well, what would be the end result here when we rotate about the line y equals -3? Well, that shape right there will be mirrored. So from the axis of revolution, the region right here, do you see how it is 1, 2, 3 units away from the axis? So when we mirror this about this axis of revolution, that region will be, or will show also 1, 2, 3 units on the other side of the region. So in this case, well, let's see. This will be, okay, yes, he's using this color. So we will have it's gonna look like this. Well, kind of like this. All right. And in this case, when we rotate this, see how it's, in this case, we are going to generate a hollow solid. All right, so that's why this time, yes, it's still the same construction, it's still the same, in a way, disk method, but because this is not a fully solid region, we have a hollow part in the middle, like you punch it from the side or something, and in this case, we are calling it the washer method, right? Because that's how washers look like, they're hollow from the center, right, from right in the middle. Okay. Now, how are we going to set up this integral? So, here is where it's going to get a little tricky. So, ultimately, we're rotating this little region right here, isn't it? So, this is what we're rotating. But in this case, we are rotating about the line y equals to -3. Well, suppose that instead we were looking at the whole solid. So in this case we're having all solid here, but what we want is to get rid of that part that turns the solid into a hollow shape. Okay, so in this case, what we're going to do is we're going to look at the very, very outermost. You can think of also a radius. Actually, if you think of it in terms of radius, yes, I think the representative rectangle will help us. So from the rotation to the outermost, that's going to be our radii. But in this case, we have two different radii. We have an outermost radius and an innermost radius. Which function would represent the outermost radius? The line or the parabola? The line, okay. So we would get this shape essentially. So, and then we are going to subtract the hollow part from the axis of rotation to the innermost, to the innermost radius. All right, it's like a birthday cake, if you will. So this is the whole birthday cake, but you just want this slice. All right, what are you going to do? Get rid of the rest. All right, just cut your slice and yes. Okay, now this is where we will define every single part right here again as a top minus bottom. So top minus bottom, and if you want to put symbols here, that's the outermost radius, innermost radius, let's call it little r, and this is the line 2x, and this is the parabola x squared. And the bottom part, it's actually the function that defines the axis of revolution, which in this case is y equals to -3. Okay, so this is what we are going to do. Let's set up everything individually. Our upper minus lower, in this case for big R, that's the upper, which is 2x minus -3, and over here lower, the inner radius, which is x squared minus -3. Okay, let's clean up the symbols. That's going to become 2x plus 3 and x squared plus 3. Okay? So the first part represents the whole birthday cake, and the second part represents on the part that we are not eating about the birthday cake. Okay. Now let's set up the integral that will find the volume for us. And well, volume That's the integral of pi, integral from a to b, and in this case, that'll be outer radius squared minus inner radius squared with respect to x, okay? And well, we just define big R and little r individually from the picture, and that's pi integral. We'll look at the limits in a second, and this will be upper, which is 2x plus 3 squared minus x squared plus 3. And let's find the limits of integration. For that, again, we need to set the two quantities together. X squared equals to x. X squared equals, x squared minus x, or rather minus 2x, equals 0. And we will solve this equation the same way we solved it in the previous example. So in this case, what is this? X times x minus 2 by the zero product property, x equals to 0 and x equals to 2. So the limits of integration are going to go from 0 to 2. And well, in this case, we're only setting up the problem, not actually evaluating the integral, because I mean, these look like simple polynomials, but I mean, it's going to take a while to square the binomials, combine the like terms, and then if the integration is fine, it's no big deal. But then the fundamental theorem is going to take a long time with the calculations. Yes?
Is that expert possibly also square?
Oh, yes. Yes, this is also square. Thank you. And let's see, it's 10:42, and I think it took us some good minutes. Did you see how long it takes to solve this problem? Well, I mean, hopefully next time when we do the remaining problems, when you get the idea, I mean, after a while, I'm going to look at one of each case. One in this case where I have the axis of rotation below the region. Next time I'm going to do one with the axis above the region, and then we're going to solve the same problem but having rotations, vertical rotations on both sides of the region. We'll see about that. All right.